Good afternoon, folks. This is your old pal Dr. K here, coming at you from the interwebs. Hey. So thanks for allowing me to record the screencast with you or for you at this point. It's just easier to do this versus getting a sub. I get to sort of give you my content the way I want you to have it, and it just makes it easier just to keep on track. All right. So let's continue on with chapter 4. And I will try and make this as bearable as possible, okay? This chapter, though, does require you to start looking at your model sets. So if you have your model sets, please pull them out, and when I return next class period, we will bring our model sets in, and I will show you how to use them to help you out with this chapter. This is the first chapter that we'll really start to learn to use and to appreciate our model sets. All right? So let's just continue on with a little bit of these nomenclature problems, and then we will go on to some other structural details of some of these molecules. All right. So as we talked about before, we were learning about substituents and parent molecules, and we ended off, I think, last time over here where we asked you to name some of these substituents on the following molecules. Here we said, if I believe this was, the parent chain here. By the way, my drawing here is going to be a little bit weird because I'm using a tablet, and it's just not easy to draw with a tablet on the screen here. So, okay. All right, so for example, if this is your parent molecule right here, which is 1, 2, 3, 4, 5, 6, 7, 8. If it's an octane, then these things off of it right here, right, are substituents. So you have a methane, or you have a methyl, and an ethyl group right here, okay? And that's if this is a straight chain, right? If this is a cyclic species, like this cyclic 7-membered ring right here, right, you have 2 ethyl groups here, and you have 1, 2, 3, 4. You have a butyl group right there, okay? So we learned how to name substituents off of parents based on nomenclature and putting the YL suffix on the alkane names, all right? All right. Some substituents have complex branches. Like this is a complex branch because it's not like this one where you have, like when this is a branch here, you have a straightforward, connectivity of only a single simple substituent. If you have something here where you have a substituent, but this substituent also has a parent to the substituent, and this is the substituent to the substituent. Crazy, huh? Right? So if you have this guy here, this whole thing is a substituent, but within the substituent you have a parent, okay? So how many carbons are highlighted in the substituent above? There's 1, 2, 3, 4, 5, right? It's improper to name it as a pentyl group because this guy here actually has a parent group here. The longest chain from here is 1, 2, 3, 4. This is actually going to be named as a butyl group, all right? For the time being. You'll see it. There's some exceptions in a very few slides, okay? All right? And notice how I start to number these things, okay? And we'll get into numbering in 1 second. But if this is a substituent off of this carbon chain right here, the number 1 carbon off of the substituent is always the point of connectivity. This carbon here is the point of connectivity to the authentic parent of the chain. All right. So this substituent is a substituent. Yes, we get that. Okay. This guy here is obviously the parent. This is the parent molecule. All right. And this is the substituent on this parent molecule. But this substituent also has its own parent. This is the parent of this. All right. So here, this is the parent of the substituent, and this is the substituent of this substituent. This is the substituent of this parent substituent. Yes, I know it's redundant and confusing, but just see if you can try and kind of follow along here. All right, it's this guy here is a parent. Parent. Oh, sorry about the crazy penmanship. Okay, so this is the parent, and this is the substituent, right? Substituent. Oh my! It's like I'm not necessarily been drinking. So this is a substituent. This whole thing right here, right? This whole thing is right here, right? This guy here, right, is the parent. Is the parent of the substituent. right? This guy here is a substituent of this guy right here, all right? So that's complete messy drawing, as if some insane person, some lunatic, scrawled it, right? Is meant to make things a little clearer, obviously, all right? So anyway, so parent, substituent, parent of the substituent, substituent of this parent's substituent. Okay, you get it? Okay, so back to the numbering. This one here is the number one. Is this one here corresponds to the carbon that is connected to the real parent, to the main parent right here. Okay, this is carbon 1 of the substituent. This is important to know that. This here is not carbon 1, right? Not carbon 1. This is going to be carbon 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. This will be carbon 6, right? This will be carbon 6, right? This guy here will be carbon 1 off of this parent. Okay, get it? All right. So this guy here is a butyl, but it's not just a butyl group. It is a 2-methyl butyl. All right, 2-methyl butyl. That's what the name of the substituent is at this point. Okay, 2-methyl butyl. All right, and here is that drawn out using text, not insane scrawling. All right. So it says right here what I was just trying to tell you, what I was just following over my word saying. Okay, so there's that. All right. So you know what? Let's just go back here and name the entire thing. All right. So this is the 2-methyl butyl group. Okay, but let's name the entire thing. This is carbon number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I start numbering the parent chain from the side where I would give the substituent the lowest possible number. But because this is centered in the smack dab in the center of this molecule, this is going to be carbon number 6. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is undecane. Undecane. Right? And this guy here is 2-methyl butyl. 2-methyl butyl. Butyl. Wow, bad. All right, 2-methyl butyl. Okay, so what is the entire name of this whole thing? I'll draw it up here. See if I don't sound like too crazy. Okay, so this is on carbon number 6. This guy here is going to be 6 dash 2 methyl butyl undecane. I'm totally sorry, but this pad is terrible. All right, so 6, which is this corresponds to this 6. So on carbon number 6, there exists 2-methyl butyl, indeed, right here. And this guy here, 6 on carbon 6, there's 2-methyl butyl, and it exists on undecane, which is right here. Okay, so this is the official, this is the real name. Okay, that's the official name of this entire molecule right there. Okay. All right, let's make life a little bit easier and hopefully not much more confusing for you. Okay. All right. So this guy here, let's check on the time here. All right. Some branches have common names that you might want to memorize. Okay, and there's that word again, memorize. Right. So here's the thing. You don't have to memorize them, but you really should, because these are actually going to make your life a little bit easier. Okay. Here we see that if we have a 3-carbon entity off of a parent chain, it's a propyl group. Okay. But let's just say you have a parent group here where and let me just point this out to you. This carbon right here, right? This guy right here is connected to, so this parent is connected to this carbon of this propyl group right here, okay? This is a CH2 group. But let's just say the parent group is attached to not this carbon, but to this carbon, like we are right here. This is called an isopropyl. Iso means same. What do you mean by same? It just means that between this side and this side, you have some sameness. You have some symmetry. All right. So instead of saying every time you have an isopropyl group, you can write down you have a 1-methyl ethyl, because obviously this guy here is 1-methyl ethyl. Let me just erase this. You have 1-methyl ethyl. Why? Because this guy here right, is 1, 2. Here's your ethyl group. And off of your ethyl group, you have a 1-methyl. So 1-methyl ethyl, like it says right down here. But instead of having to always write this 1-methyl ethyl out, you might just be able to say it's an isopropyl group. Isopropyl group. Notice there's no numbers, there's no other confusion there, right? This is just a very short-handed way to say the substituent, which is very kind of cool, actually, if you ask me. All right. Let me just make sure that you can remember how you can get to this, right? All right. So how do we remember it's isopropyl? Okay. When here it says it's an ethyl group here. Well, if it's an isopropyl group, if you're using this still semi-okay IUPAC-ish way to say this substituent, you can always remember this name isopropyl by saying there is 1, 2, 3 carbons here. So 3 carbons is a propyl or a propane type of a group, right? And it is connected in a carbon that has some symmetry to it. So this has some symmetrical elements to it, and it has 3 carbons here. Okay, so here's the symmetrical thing with the 3 carbons, with the 3-carbon name to it. Okay, so isopropyl. So instead of saying 1-methyl ethyl, which is the official IUPAC nomenclature, you can get by saying, instead of an ethyl group here, you can just say it's a propyl group, but it has an iso connectivity because the iso means it's in the middle, right? It has some symmetry to it, all right? So 1-methyl ethyl is isopropyl. This is, I think, probably by far the most popular substituent name that you'll be using, in this coursework, all right? So isopropyl is huge, all right? And you'll see how much we use it from here on out, okay? So here's one, and here's some other ones. Here's the butyl family. Okay, the butyl family. Okay, you have sec-butyl. All right. Notice here, this is butyl 1, 2, 3, 4. This is a butyl group. It's also known as a. Let me take this away. Also known as N-butyl. N means normal butyl, which means that this is a normal, plain old connectivity to the end of a butane, right? So you can say N-butyl or butyl, and we'll all know what you're saying. Here's something else. Sec-butyl, which is 1-methylpropyl. So this is the systematic IUPAC name that you can get to, right? Sec-butyl refers to this carbon right here. This carbon right here, you will soon know as it being a secondary carbon. All right. This is a secondary carbon. This is a primary carbon. This is another secondary carbon. Here's a primary carbon. All right. We will learn what these secondary and tertiaries means. You know what? Let's talk about it right now. Okay. So CH3. Okay, with a little hook. All right, which is for the substituent. This is a methyl, obviously. Right. It's a methyl. All right. But let's just say you have a carbon here that is attached to another. You have another carbon attached to it, but still going to be on the end of something. All right, CH2. Here's your hook for the substituent. This guy here is called a primary. A primary. Primary, and the way we say, and the way we also write primary is with a 1 with a little degree sign there. All right, that's a primary. This guy here, and we'll right now we'll just draw it all in bond line notation to save time. This guy here, if it's a secondary carbon with a hook on it, this carbon right here is a secondary. Secondary, hey, this is where the sec comes from. Secondary. Secondary is a 2 with a little degree sign right there. And tertiary, right? Tertiary is something. We'll have a carbon here. So this secondary is a carbon that's attached to 2 carbons. Primary is a carbon that's attached to 1 carbon. Secondary, a carbon attached to 2 carbons. And this guy here is a carbon with a hook that's attached to 1, 2, 3 carbons. This guy here is a tertiary. A tertiary, all right? Tertiary, or 3 degrees. 3 little degrees sign over there, okay? And that would be a tertiary or a tert. All right? So let's just see up here what we mean by all these things. Let's just see some examples, right? Isobutyl 2-methylpropyl. So iso, remember, same, right? Iso, same. So, you know what? Let's just go back here. Sec-butyl. 1, 2, 3, 4. 4 is butane, all right? So this is a butyl group here, and it has a secondary connectivity, which is that carbon right there. Right carbon. It looks like a carbon that has two carbons attached to it, right? This would be carbon number 1. This would be carbon number 2 in terms of how many carbons are attached to it. All right. So there's your secondary carbon. So it's a sec-butyl. This guy here is an isobutyl. Iso. Now look at this. Why is it butyl? 1, 2, 3, 4. Still butyl. Still 4. But why iso? Because iso means you have a symmetry of connectivity there. Okay. So isobutyl. It's the same butyl. It's a butyl group here that has some symmetry attached to it. Okay, and your final type of butyl group that you can have would be a tertiary butyl or a tert butyl. 1, 2, 3, 4 carbons with the tertiary connectivity right there. Right, tertiary is right there. Right, tert butyl group. Tert butyl, again, another important substituent name that you'll be using. My guess for you. The three things that you'll be using a lot here with these substituent names would be the methyl, would be isopropyl, and tert butyl. These are the 3 biggies that you'll just see over and over and over again because so many reagents use them. Use these type of connectivities. Okay, it's a very useful type of connectivity. Here's some lesser used ones. Here's the pentyl group here. Okay, pentyl from 5. All right, 1, 2, 3, 4, and 5. Isopentyl. All right, isopentyl right here. Iso, again, same. Pentyl means 5. 1, 2, 3, 4, 5. The same comes from the fact that you have, even though it's drawn in a weirdly bent position this way, what's up here is the same as what's down here. All right, isopentyl. Isoamyl, you almost never, well, you hear it a lot in isoamyl nitrate, of course, but it's a sort of a semi-phased out sort of a name. It's an older name. This is the amyl group here, which again we really don't. It's still used in some very old textbooks, and I never use it. Your textbook almost never uses it. I think never uses it. But isopentyl is used, or 3-methylbutyl. But honestly, these things here really aren't used that much. Maybe neopentyl. Maybe neopentyl. Why is it neo? Neo officially means new. There's that, and it's also the dude from the Matrix. So, I don't know. You know what? I'm going to tell you right now. I don't know exactly what neo signifies. Neo just means new as far as I'm concerned, or as far as I know. All right? Because I'd say, well, this would also be like, shouldn't this also be like an isopentyl type of a thing? Well, maybe because this is isopentyl, you have to have another one that's not isopentyl, but has a different type of connectivity. Because this isopentyl here has a primary connectivity here. And this neopentyl also has a primary connectivity, but these other connectivities are different back here. So maybe neo does mean new, because we already have iso, so maybe we have another type of thing. Okay, and that's where this neopentyl comes in, and that's used sometimes. But again, you'll come across that a half a dozen times maybe in your entire year's tenure here with me. All right, so there's that. All right, so naming the compounds, alkanes, numbering the parent chain, just like we talked about before. Very simple stuff here, okay? Number in sequence the consecutive carbons in the parent chain and assign a locant to each substituent. The number, or locant, is a number that's used to tell me where substituents are within the parent chain, okay? The locant is used to communicate where each substituent is located, all right? These two isomers here are these two molecules are isomers. They're constitutional isomers. They're different in their connectivity, but they have the same molecular formula. Okay, so you can't just say, well, I have a C6 H something or other, right? You have to say, and now I have a 2-methylpentane or 3-methylpentane. Okay, why? Because this methyl here is attached to the number 2 carbon right here, and this carbon here, this methyl here, is attached to the number 3 carbon. Notice how I said before, like I said before, you start numbering the parent chain at the end of the carbon chain. that you can give the substituent the lowest possible locant number, or start numbering from the closest substituent. That's what, so you want to start numbering here. And here it doesn't really make a difference at all because 3 is in the center, so you can number from here or from here. Okay, but since this methyl is closer to this side here, you start numbering from this side. Hence, this is why this is 2-methylpentane, 2-methylpentane. This guy here is 3-methylpentane. 3 here is right in the smack dab. So you can number this side 1 or this side 1. But if it's not symmetrically substituted, then you have to choose whichever side is the closest one that you have the substituent on. Okay. All right. So here's again. This is like what I said before. If one substituent is present, number the parent so the substituent has the lowest possible number. Here's a correct way where this methyl has 2. This guy here is incorrect, right? Because this substituent here is numbered 6 because they numbered from the other side here. So 1, 2, 3, 4, 5, 6, 7. So this guy here is good, and this guy here is bunk. Okay, this is sort of fun. It's scribble. No. Oh, sorry. Sad face. I don't know why I'll just draw some hair on him. This is getting really wow. Now I'm like a crazy 3-year-old. Okay, here's this. All right. When multiple substituents are present, number the parent chain to give the first substituent the lowest number possible. All right. So here's the correct way. Here, 2, 5, 5 beats 3, 3, 6. How do we know what these are? Okay, so this is obviously the parent chain right here from 1 to 7. From 1 to 7, so that's not disputed. All right, what is disputed is where you start numbering from. Do you start numbering from this side here, or start numbering from this side here? You obviously start numbering from this side, right? Because this methyl is closer to this side. So here, this guy here 2 is closer to this side here than it is than anything is on this side. If you were to start numbering from this side here, your closest substituents, even though you have 2 of them, would be at the 3s. All right, and even though there are 2 3s here, 2 3 methyl groups here, right? This guy here is the lower number wins. That's as simple as it is. There's no, as far as I know, there's no caveat to that. Okay. That's some good. Let's call it coffee. All right. All right, if there is a tie, then number the parent chain so that the second locant gets the lowest number possible. Okay, so if there's a tie here, so the correct here is 1, so the correct number here is 2, 3, 6, right? All right, and this guy here, right? So the 2's are the same. All right, but now we have to go to the 3's. So 1, 2, 3. So 3 here, you have a 2, 3, 6 substitution. 2, 3, 6. 2, 3, 6 substitution versus the 2, 5, 6. So this guy here, right? So 3 is lower than 5. So this guy here wins, right? And this guy here is the wrong way to do it. Okay? So again, it's pretty common sense. And again, what do you think is going to happen to that very last value? Okay, if it wasn't 6, right, that'd be a different story, right? So if one of them was lower, you'd always pick that lower one. Okay, if you always want to be able to break a tie when possible. Okay. All right, the same rules apply for cycloalkanes. Pardon me. Okay. So the correct number here, so the correct thing here is you have a 1, 1, 3 substitution pattern here versus a 1, 3, 3. All right, so you start numbering from here to here, okay? Not from here to there. That's wrong. Okay, and there's also one more thing I want to show you. Okay, notice, and again, this is common sense. Well, this is common sense after you learn it, all right? But right now, we'll assume that, you know, we're still building your intuition about organic nomenclature, okay? Which is fair to say. I'm sorry about this being sort of wacko. All right. So there's a drunken trimethylcyclohexane. Notice this is going to be carbon 1. And because this is carbon 1 because it is the most substituted. And notice how I did not start numbering from here to 2 to 3 to 4 to 5. Notice how I did not say this is 1, 2, 3, 4, 5. I did not say that, right? The shortest distance between any 2 points, or in this case, any 2 carbons, is essentially that. Well, not a straight line. That would be wrong. All right, but choose the shortest distance between the numbers of carbons that have substituents on them, if possible. Okay, so here's correct. This is 1, 2, 3 going this direction, not this direction. This is incorrect because it goes the opposite way from here to here. It's supposed to go from the most substituted to the least substituted. Okay, so that's how that goes. All right, here's where it gets a little bit, it seems like there's a whole lot of rules to memorize and stuff, but really it's going to make sense. Like after you do like your first, like your first 5 or 6 questions for nomenclature, and especially after you come to my discussions, you'll be able to see what this is going to be all about. I mean, just after a little bit of practice, you'll get very good at this very fast, all right? Especially this group, all right? So, to assemble the complete name, assign a locant to each substituent and list them before the parent chain in alphabetical order, okay? Here's something that's important. A prefix is used if multiple substituents are identical, all right? Prefixes, however, like this, are not used for alphabetical purposes, except for iso, because who would we be if we didn't have annoying exceptions? Okay, name the cycloalkanes. So we will not name this one, but we will name this one. The parent chain is a what again? All right, it is a cyclohexane. All right, you have 2 methyls here and 1 methyl here, so you have a 1, 1, 3 trimethyl. This should all be one word. All right. 113 trimethyl cyclohexane. So let me just try 113 trimethyl cyclohexane. Okay? So this is the real name of this thing, okay? 113, all right? And this is all one word, all right? And so there's nothing here to alphabetize, but we will do a few examples probably in a minute, but we will definitely do some during next class period, okay? All right, so here's a summary of just the alkanes. And again, when you start learning this, the more advanced ones, we will just kind of, come in with some other details about this other nomenclature, and we will just add on to your knowledge of this alkane nomenclature. Okay, so when we learn about alkenes or alkynes, we'll just add on to your base knowledge of this. Okay, so ID the parent chain, longest chains of carbons, either as acyclic or a cyclic species. Identify the substituents or the side chain. Number the parent chain and assign a locant number to each substituent and a prefix if necessary. And give the first substituent the lowest possible number. List the number of substituents before the parent chain in alphabetical order. Ignore prefixes except for iso. When ignoring alphabetically, please do Skill Builder 4.4, but also do everything in your chapter that we cover here. Okay, and everything that we cover here will be more or less at the top of each of these slides, right? So if I skip over, for example, 4.7, which I don't believe I do, but if I were to skip over a section, then feel free to ignore that section in your studies, because I won't deal with that during, for any exams or anything like that too. But I don't skip much, but I just skip some stuff, and I do add in a lot of things. Okay, so just stay close to your notes here. Okay. All right. Name the following molecule. All right. Let's get the parent chain here. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9. 1, 2, 3, 4, 5, 6, 7. It's 7. So that's a no. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, obviously this is going to be one of these guys here, okay? So this is going to be a 9. And I'm just going to pick this side here to go with. All right, so I'm just going to list out what I know here, okay? Okay, so this is 9, right? So it's a nonane. Nonane. Okay. Okay, and let's just list out these things. This is an isopropyl group. See, I've already jettisoned the 1-methyl ethyl, right? This is isopropyl. right? Isopropyl, we can use that. I is going to be used for the alphabetizing of it. Ethyl is here, and methyl is here. Okay, A, B, C, D, E, F, G, 1, H, I, J, K, 2, L, M, 3. All right. See, the alphabet song even comes in handy in sophomore organic. Isn't that totally awesome? All right. So now we've seen that the way we've had to list them in order. Right. Now we just have one more thing to do. Assign each of the locant numbers. Do we start from this side here, or do we start from this side here? Do we know? What is the? Do we know that? The Riddler. The Riddler. No, I'm sorry. Okay. Do we know which here or here? All right. My guess is going to be this side, right? Ding, 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 ding. Why? Because 1, 2, you can give this methyl the 2 locant, where 1, 2, 3, you can give this ethyl the 3 locant. So this guy here is going to be, I think, the locant for us, okay? So this is going to be this guy here is going to be the locant number 2, 2, 3, 4, 5, 6, and 7. There's that. All right. So that is the locant. But so now we ignore those until we have to. Did I make sure everything's right there? Yes. Okay. Now, okay. So now we have ethyl, methyl, isopropyl. Oh, sorry, methyl. We have 2 methyls, huh? We have 2 methyls. So these are both going to be 3. We have 2 methyls, don't we? We have a dimethyl situation going on here. All right. So how do we start labeling them? Let's just start. Let's name this beast down here. We'll just start with here because we know what to do. Okay. So ethyl is first one. Second is isopropyl. And these guys here are going to be not methyls but dimethyls. But still, the D in the dimethyl does not get alphabetized. Only the I in isopropyl does. All right. So we start here. We start off with 7-ethyl. Locate number first. 7-ethyl. 7-ethyl. Good. We got that. Boom. 7-ethyl. 2. Okay. We have 5 isopropyl. 5 isopropyl. Boom. Okay. And then we have a 2,6 dimethyl. A 2,6 dimethyl. All right. And that's what we can do, right? We can do, so 7-ethyl, 5 isopropyl. We have a 2,6 dimethyl. So 2, 6 hyphen dimethyl. Dimethyl. And then no dash here. Nonane. Nonane. See? 7-ethyl, 5 isopropyl, 2,6 dimethyl nonane. All right? Cool stuff. That's the name of this thing, I believe, right there. All right, so you see how even though it gets hairy, and look at this impressive name that we came up with, which is completely awesome and it's systematic. So why is this so weird to you right now? This is the first time you've ever learned a systematic nomenclature. Everybody you know has been like, Angelo or Mikey or Mark or Miley or one of those. I don't know why I'm hanging on the M's at this point. But all the names that you know, right, have been non-systematic, right? It's up to now, and so now names start meaning something. And to name things in organic chemistry means you have to systematize a type of nomenclature. This is what systemizing a nomenclature looks like: putting numbers and alphabetical names around. Okay. What's so awesome about this? If you didn't have this guy right there and you just had the name, you could reconstitute the structure of this based on the name. And here's what I recommend. Every time you have a problem that says, give me the IUPAC name for this, do that IUPAC, draw out that IUPAC name. Okay? Then what you should do is go back and then erase the structure that you got the name from, and then reconstitute the drawing just based on your name. So draw your nonane, right? And then off of your nonane, put an ethyl where the 7 carbon is, and the 5 where and put an isopropyl where the 5 carbon is, and put 2 methyls where the 2 6 carbons are. Okay, that's how to figure it out. All right. So again, make every study thing that you do, work double duty for you if possible. Okay. So don't just draw the name for it, but also reconstitute the structure for it. Okay. Draw the bond line representation for 1 tert-butyl, 2 ethyl, 4 methyl, 3 cyclopentyl, cyclohexane, okay? So do that. So let's do this really quickly. Okay. So what is the parent? It's a cyclohexane. Cyclohexane. Draw the bond line representation for 1-tert-butyl. Okay. So we draw the cyclohexane. Okay, no problem. We'll just draw the 1-tert-butyl in any position. We'll say this is 1. Here's 1-tert-butyl. All right. 2-ethyl. Boop boop. So 1-tert-butyl, 2-ethyl. Okay, so we did this. 4-methyl. 1, 2, 3, 4-methyl. Boop. 3-cyclopentyl. Pentyl, right? Cyclopentyl. That's 5. Almost cyclopropyl. Okay, cyclopentyl. There you go. That's the dealie, right there. All right. So you see, it's a systematic way of drawing something and naming something. You can reconstitute, your structures from a name. All right. Awesome stuff. All right. So there are many compounds with. So that's So we talked about rings and stuff like that before, but we never talked about anything that's more complicated than a ring. All right. Or just a long straight chain. There's something here called bicyclic compounds. So we've learned about cyclic compounds. Cyclic compounds are just regular, cycloalkanes. There's a 6-membered ring. Here's a 5-membered ring, and so forth and so on. But bicyclic compounds, right? This means that you have 2 compounds that are cyclic that are smushed together, right? That are just smushed together. So imagine this guy here, which looks like a cyclohexane with a little bridge on it, right? A bridge on it. Yeah, that's something. But what you have here really is you have a 5-carbon ring, a 5-membered ring here, and a 5-membered ring here also, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 5-membered rings here, okay? And the other way to look at it is this other way. So imagine this guy here, but sort of turned a little bit, turned like 45 degrees. Turned 45 degrees. And this is, again, where your model set's going to come in. And so when I see you next time on Wednesday, I'll bring in my model set. You bring in yours, and we can play with our toys together, okay? All right. This is important to know. To name a bicyclic compound, include the prefix bicyclo. Okay. Notice how in this previous slide, this guy here was a cyclohexane for the single ring that was right here. This guy here is a bicyclo. So whenever you have this kind of situation right here, make sure that you write bicyclo beforehand, okay? So bicyclo in front of the normal name ending in ane. For example, the compounds below could both be named bicycloheptane, right? They are both bicycloheptanes. But there's something that's very different about them. Their connectivity is different, okay? And actually, the nomenclature here is really easy and very satisfying, because once you can do this, you end up making this name that looks so crazy complicated, but it's completely correct, and you'll be able to again reconstitute this compound from your name. All right. So what is the difference between the 2 carbons below here? It is how many carbons are between these guys right here. These are called the bridgehead carbons. All right. Those are called bridgehead carbons. The number of carbons between the bridgeheads is different. So let's count them. So between these 2 carbons here, we have 3 sets of numbers to worry about. Okay, we have 1, 2, 3. So that there's here you have 3 carbons. Here you have 1 carbon. Here you have 1 carbon. See? Ooh, look at this. 3, 1, 1. Cool, huh? What is your name here? Bicyclo. Always first for bicyclic compounds. Bicyclo. 3,3,1 heptane. How could it be heptane? What are you talking about? Isn't it a cycloheptane? It is a cycloheptane. Bicycloheptane. What do you mean by heptane? 1, 2, 3, 4, 5, 6, 7. 7 total carbons. Heptane, okay? Heptane, 7 total carbons. How else can we find out if it's a heptane? All right? So what we can do is that we can take these 3 numbers right here and then add 2. 1, 2, 3, 4, 5 plus 2 gives us heptane. Cool beans, no? So So let's go about the entire way to name these things. Okay, how to name these things is you first start by writing bicyclo. Check, we got that. All right. Then over here, what we can do is we start counting the carbons all around these bridgehead carbons, but we don't count the bridgehead carbons. We don't count them. Those are left out. All right. There is 1, 1, 2, 1, 2. There's 1. All right. And then we arrange these numbers here, right? The 2. So there's 2 carbons here. There's 2 carbons here. There's 1 carbon here. So there's 2 carbons total here. 1 carbon totally here. And there's 2 carbons totally here. All right. We arrange this in order of largest number to smallest number. So 2, 2, 1. So 2, 2, 1. Bicyclo, which we already know from before, 2, 2, 1. Heptane. Heptane is a total carbon count, or this number count plus 2. Okay, cool. See, 1, 2, 3, 1, 1. So this is going to be 3, 1, 1. So bicyclo, 3, 1, 1. Heptane. All right. So first write bicyclo, then put the numbers in order from largest to smallest, and then write the parent name at the very, very, very end. Okay, making sure to put these carbons back into the name, right? When you start putting in the parent name. Okay. All right. Here's a little bit more difficult, but not too bad. Okay. It gets a little bit confusing, and we will do a lot of these during discussion, so don't you worry about it. Okay. All right. Let me see what time it is. How we're doing on time here. We're good. Okay. To number the bicyclic parent chain, start at a bridgehead carbon and number the longest chain connector first. All right. So let's do this one here. Okay. Okay. Longest carbon chain connectors first. Okay. Didn't we just say it doesn't really matter what the numbering really was around these bridgehead carbons? It matters if you have a substituent. That's what the difference is in this case. All right. If you have a substituent, it does matter. Okay. So here you start numbering at a bridgehead carbon such that you would go through the longest possible parent chain. So 1, 2, 3, 4, 5. This is the longest possible parent chain right there. Okay. All right. And then from there, 1, 2, 3, 4, 5, and then you continue numbering through the next largest. This guy here is a 3 carbon chain. So this is the one you start numbering first. Then you continue on to the second largest, which is 2 carbons. So 1, 2, 3, 4, 5, 6, 7, right? And then you end up with your smallest carbon bridge right there, right? And you end up with that number. Okay. So 1, 2, 3, 4, 5. You continue on here, 6, 7, and then you end up there with 8. Okay. So what do you think that this beast would be called? Okay. This guy here would be called. Let's see if we can have this. All right. We'll write this out over here. All right. So a bicyclo. So we'll need some space over here. Well, you know what? This guy here is going to be 8. This is an 8-methyl. So we'll just start here. 8. You know what? Bicyclo 8 or 8-bicyclo. 8-methyl bicyclo. I believe it's going to be 8-methyl. 8-methyl bicyclo. Bicyclo, right? 3, 2, 1. 3.2.1. 1, 2, 3, 4, 5, 6, right? And then what's going to be the parent chain here? So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be octane. All right, octane. And here it tells you everything you need to know about what the compound is, okay? Here you have an 8-methyl, which is off over here. You have a bicyclo, which is a bicyclic ring here, and it is going to be a 3, 2, 1 species here, separated by these little periods, and it's an octane, all right? And you can count the parent chain here like this, or you can just start, or you can just add 2 to your bracketed numbers right there. Okay. This is extremely easy to get confused about. Okay, so please be very, very, very careful. Okay. Here it's going to be, here, without violating rule one, rule one above, give the substituents the lowest possible numbers, if at all possible. Okay, so here is going to be 1, 2, 3, 4, 5. This guy here is going to be 6. So why did we use this one here versus this one here? It's the same exact rule that we knew from before. We want to make sure that we don't give the substituent the highest possible locant number. If you have a choice, and you didn't have a choice here, you don't have a choice here because carbon 8 is carbon 8 period. All right, but here you either can start numbering from here to this side or from there to this side. If you were to number from here, 1, 2, 3, 4, 5, 6, 7, 7 here is larger than 6. So if you start numbering from this side, 1, 2, 3, 4, 5, 6. All right, 6 here is lower than 7. This makes that correct. Okay, so this is the thing that you want to concern yourself with, making sure that that these rules don't get broken. And these rules, even from the very simple straight chain alkanes, right, they hold, right? So again, keep the locant numbers to the lowest possible, if possible, unlike here, which is not possible at all. Okay. Okay. Again, here you will not get these kind of Okay, let me make you feel better, sort of in a way. You won't understand this concept from that previous slide, even if you followed all of my words that I just said. This is all about practice. So again, practice from your book, or come to discussion. Okay, and I will give you much more to practice on. Okay, and so from there we will be able to hone your skills. And again, it seems crazy and it seems like it's going to take forever to learn this, and it won't. Give me another hour in your discussion, and you will be well on your way. Okay, just make sure you bring your brains with you, and stay focused, and we can get you to this. Okay, so this is not going to be a problem at all. Just make sure that you're with me. Okay, all right. Constitutional isomers. Recall that isomers are different structures made from the same atoms. Isomers are not identical. They have the same form. Constitutional isomers are different in connectivity. All right. So here's 2 hexane isomers. All right. This is the straight chain N-hexane, and this is the 2-methyl pentane hexane isomer. Okay. So be able to draw multiple constitutional isomers of these things here. Okay, if possible. Know the systematic way to go about it. Okay. What's the systematic way to go about it? Well, there's only one way to draw that guy, so there's that. But make sure that that there's 2 possible isomers of this methyl pentane. There's that isomer, and of course, there's that isomer. There's the 2-methyl pentane. There's also the 3-methyl pentane. All right, and then not to mention at all about the butanes. Right, the butanes here have all kinds of different isomers. All right. So just make sure that you can get to all those. All right. And so there's a lot more there, okay? So just make sure that you are solid on this concept. All right. How can you recognize if 2 molecules are isomers? This is, I think you probably can get this pretty obviously right now, okay? If all these guys here are sp3 hybridized, that means that there's no double bonds or triple bonds that are keeping them from spinning around. So I think that this guy here is also this guy here. They are not really... they're not really characterized as isomers at all. Okay, why? Because these guys here, these carbon bonds right here, are very, very, very they have a lot of bond rotation to them, and so they really don't. It doesn't really count as some sort of an isolatable compound. All right, if you can rotate these bonds around each other, then you have then you have essentially the same molecule. There's a lot of conformational rotation around these things here, and so this guy here is like this shape for like a billionths of a second, okay? And then it goes to something that looks like this. And then it goes to something that looks like maybe this guy here is flipped up, okay? So if you have sp3 hybridized carbons, you have all kinds of flipping that can go around those single bonds, okay? And again, here's a test to see if any of these two molecules here are identical. Can you flip these molecules such that they are identical, such that they can superimpose upon themselves, right? And also name them too. If there's only one way to name them, and the names are identical, then you know that's what it is. Okay. All right. Flip one of the molecules in 3D and rotate around this single bond here. Again, this is I'm taking probably too much time on this, but these guys here are the same, obviously. If you take this guy here, do a bond rotation around here, you end up with this, then do the spatial rotation where you pivot this whole thing through this axis, right, through this axis, right, through this axis right there, then you end up getting this guy here, right, and if you pivot it this way, right, you end up getting this guy right there, right. So we bring this up because the next thing that we're going to be learning is going to be some pretty intense spatial relationships. Okay, so, and again, also, if you don't believe in doing that, just go about using just using the nomenclature method. If the two things have the same nomenclature, then they are the same compound. Okay, which method for testing whether molecules are identical is probably more surefire? This of course is the way to be 1,000%. 1,000%. That doesn't make sense. 100% sure, right? 100% sure that these guys here are the exact same compounds. Okay. Here's where I say you can skip this stuff. Okay. Sources and uses of alkenes. This is very cool stuff and useful to know, but we're not going to cover most of this. And don't do the homework problems associated with these sections because I'm not going to ask you any of these things on the exam because again we have bigger fish to fry. And this guy is great, but it's not what I really necessarily care about you to know, okay? But it is important. If you want to know it, please feel free to read it and stuff like that. And again, the more you know, the more you can intimidate your non-science friends. All right, so it's always a fringe benefit of learning this stuff, okay? So anyway, at room temperature, this is the brief summary here. At room temperature, small alkenes of 1 to 4 carbons are gases. Okay, like for example, your butane letter from your Zippo, right? Butane is a liquid, right? But the butane here has also some other stuff in it as well. Okay, but when you buy some propane, buy some propane for your gas grill. There's that. Medium size are liquids more or less. Large alkanes are oils, okay, and extra large alkanes are like solids, like tar and waxes, okay, and very large alkanes are like polymers, okay. And so the things that, like when you go and get for example, your legs waxed or whatever, or you do some cosmetic waxing. The waxes that they use are very large alkanes, okay, and they heat them up and they cool it down. And they use that wax to rip the follicles right off your body. So that's what they use there. All right. What type of properties would you expect such polymers to possess if we're talking about this guy here? Well, the polymers here would be, again, very, very, very hard. And a lot of tensile strength there, right? And why would they have this? And consider London forces. If they're not carbon bonds, if carbon bonds aren't the only things that's associated with bond strengths of all these mixtures of alkanes, what else can possibly be there? Well, the London forces, as we learned from the first chapter, you might be able to see two very large molecules be able to temporarily shift their polarity such that one end of the molecule will be more negative and one end will be more positive, such that they might have some sort of magnetic attraction between each other. Okay, so there's some London forces action going on there too. So not just the carbon-carbon bonding type of things from sp3 hybridization, but also London forces as well. Okay, Newman. All right, this is where it gets awesomely fun. I can barely contain myself. I almost don't even want to do this by screencast. Maybe just a few more minutes, and then we'll hit this again when I see you next time. we knew that single bonds in molecules can rotate. We know this already from a few slides ago. Different rotational states are called conformers, all right? Conformers or conformations. Things that are differing that differ in their conformations are called conformers. 3D rotational conformations are difficult to represent on a 2D paper, but it's possible, and we have a lot of things to be able to show that we can do that. So it's useful to make a molecular model to help you visualize these structures. So here are 3 ways to represent ethane, for example. All right, here's one other way to represent ethane, which is really boring. There's your ethane for you, right? CH3, there's your bond line, but it doesn't tell you anything about where the hydrogens are, right? So here, wedge and dash. It's called the wedge and dash. As you know, here's your wedges, and there's your dashed lines right there. Sawhorse, which is just if you take your wedge and dash and you pivot it a little bit where it's coming out at you a little bit more, this way, right? You'll be able to see this sawhorse, and I'll bring in take in my set on Wednesday to show you. And then ultimately, if you look down the barrel of this sawhorse, right here, or look down the barrel of this wedge and dash right there, you end up getting the Newman projection. This type of thing is so important and it's so popular to use, right? It's so very, very, very helpful. But this is a really weird way to look at a molecule. But there's a convention here that we will learn. I want you to notice something here, okay? These hydrogens here, these blue hydrogens right here, here, and here, are indeed these hydrogens right there, all right? These red hydrogens are indeed these red hydrogens over there. This carbon right there that I will star, quote unquote star. It's a euphemistic star, all right? That carbon right there is really this carbon right there. And this carbon right here that I will put in a box is really this carbon right there. That circle right there. Well, I should draw a circle, right? This circle right there is really this carbon right there. Crazy, right? To show the large carbon being the one that's furthest away, but it's a Newman projection, right? And it's something that that it's sort of a convention, okay? And this is Newman the Postman. This is from an old-timey comedy show called the Seinfeld Show. It's a very funny show. If you guys, I hope you guys are still watching it. It still holds up. I know this is 20 years later or whatever, but it's awesome and it still holds up. It's the greatest thing ever. All right, so Newman. Look directly. So how do you draw a Newman? Look directly down the CC single bond axis. This is where it especially is helpful to have a model, a model set, that is. Although if you're lucky enough to have or if you're lucky or unlucky enough to have a model hanging around your apartment, cool for you. But they might not help you with this. Although they might help you with other things. I guess I'll just stop there because it's just gonna incriminate me. All right. So anyway. So have your model sets handy, okay? Have your model sets handy, okay? Because so look down the down the CC single bond axis right here, all right? And as you look down here, this is something that I will train you how to see. This carbon here, remember, is the circular carbon right here. That's this one right there. Again, counterintuitive, especially based on what we already know about force perspective. Still, though, this is not about force perspective. It's all about the type, the principles of learning how to do a Newman projection. Okay, so the front carbon here is noted by a point with the 3 hydrogens coming out at you, and these guys here are noted by a circle with these other 3 hydrogens coming out at these other angles, in between these other 3 hydrogens. Okay. So that's how to draw this, okay? And again, it's a lot better to show you in person. So probably going to be. So why is this? I tried to find a picture of this eyeball on the internet, and the only thing I could find is this half crazed eyeball, and it just means it's just so severe. It just, I don't know. I think it's in some sort of a weird love triangle or love projection or something. I have no idea. But anyway, it just looks creepy and intense. So I was like, love me, damn you. All right, there's that. All right, draw a Newman projection for the following molecule. Let me show you how I would do this, okay? All right, I'm going to draw this here, and then we'll stop here for the day, and then we'll pick this up again on Monday. On, what's today's date? is it today's Monday, right? No, so Wednesday. That we'll pick it up on Wednesday. All right. So we'll do this. Look. All right. So here's what I look. Here's what I see when I see this. I see not just this 1, 2, 3, 4 carbon butane here, but I see also, right? I see also that we have a proton here, a hydrogen here coming out at you, right? And this other hydrogen here going away from you. All right. I see something else too that's coming out at you over here. What else do I see that's coming out at you over here? Well, remember, we also have another hydrogen coming out at you here, right? All right, let me complete the way this thing looks, right? Remember, at the end of this line here is a CH3, you know that. Blech. This guy here is also CH3, right there, all right? All right, so if I'm looking down the barrel of it right here, what's pointing down at me is this methyl, all right? So I'm going to draw a generic staggered Newman projection, all right? Circle in the back, all right? This guy here is pointing down, and these guys here are pointing this way, just because that's the convention. So I'm going to draw it that way. All right, so this guy here is pointing down, so I'll just draw the CH3. All right, there's that. I will draw this hydrogen here. Since this is coming out of the screen at you, and I'm looking over here, and essentially my body is in the screen, is in the plane of the screen. This guy here is coming out at you. So this guy here, if I am this eyeball, I'm a brown. My eyes are brown, by the way. It's a blue, crazy blue way. Anyway, this hydrogen here is coming. It would be to my right, right? So it would be right here. So this HA, for example, right, would be right there. All right. And this guy here is going through the screen, right? So it would be right there. And we can just, if you put that being B, we can put that being B there as well. Okay. So that's the front carbon. The front carbon's already taken care of. So the carbon bond here is pointing downwards. We have that. The HA is to my right. The HB is to my left. HA is to my right. HB to my left. All right, great. Now, if it's a Newman projection and it's a staggered conformation, that means it can only be one way how it's drawn, right? We will put this methyl up like so. We'll put, a bond up like so, and two other bonds in between, like so. All right. So if this carbon-chlorine bond here is pointing up here, where will it be over here? If you said that it's going to be right here, you would be correct. All right. Notice CH3 carbon, no CH3 carbon carbon Cl is down and up. Look, this is all in the same plane. CH3 carbon carbon Cl, right? CH3 carbon carbon Cl. All right. So if this chlorine is up like so, what will be to my right? What should be to my right? Right? What is coming out at me? Indeed, the hydrogen is. All right. And this guy here is the only thing that's left, and this guy here would be going through the screen. So CH3. How would it look to, so, and we are done and we are good, right? So how would it look if the observer were viewing it from the opposite direction? So let's just say you take your eyeball, all right? Oh, I drew an opposite eyeball. It's weird. Why did I even do that? All right, so copy this down, all right, and I'm going to erase it. Boop, boop. I'm going to put eyeball here. Here's my eyeball. Here's my weird, I don't even know what the hell I'm drawing anymore. It's like some alien. This is eyelashes, I guess. Crazy. Zoo. Oh, it's good. All right, bloodshot eyes, of course, right? Because, you know, the Kahlua. Anyway, and I'm looking this way. Now draw the other Newman projection from the other side, okay? So draw it not just from here, which is what we already did, but draw it now from the other side too. And do this, again, to give yourself more practice. All right? Do that to give yourself more practice. Now, when I see you on Wednesday, make sure to have your model sets with you, okay? Because I want to be able to play with the models and show you what I'm looking at when I'm looking at these things, okay? And I'll show you how to manipulate these things a little bit better, okay? And we'll have some fun with that. All right. Thanks, everybody. Sorry I couldn't make it in today. There was lots of stuff going on that I had to deal with. All right. I will see you soon. Later on. Bye-bye.